Welcome to the video on quantifying acids and bases, specifically Ka and pKa, in determining how acidic a compound is. There are two ways that we could talk about acidity. The first is using the pKa value, which is an actual number that tells us how likely that compound is to give up its proton. That's called quantitative. The second way is qualitative. If something is acidic, it will give up a proton. So in terms of qualitative description, we're going to look at that conjugate base and we're going to say, is that conjugate base stable? If the conjugate base is stable, then that acid is very likely to give up that proton because it creates an entity that is stable. This video is going to focus on the quantitative aspect of acids and bases, i.e. Ka and pKa. Recall from general chemistry, we had a list of strong acids that would completely dissociate, and then everything else was considered a weak acid because it partially dissociated. In this course, we're going to entertain all of those acids, and we're going to be talking about how likely are they to give up a proton based on their pKa. But in order to talk about pKa, we have to take a step back and talk about equilibrium. Quantitative strength is going to give us a number to compare how strong an acid is. Remember that the Ka is the acid dissociation constant for an acid dissolved in water, and it is the measurement of the acid's strength when water is the base. Remember, we have an acid put in water. What we get is the conjugate base, which is A minus, and then we have protonated water. Remember back when we discussed equilibrium in general chemistry, we have KEQ is the concentration of the products raised to the power of the coefficient over the concentration of the reactants raised to the power of the coefficient. And here our coefficients are all 1, so there's no power. So we have the concentration of the products over the concentration of the reactants. When we're talking about Ka, however, we're going to simplify it and we're going to remove water. And so the value of Ka includes the water term. And so KEQ, water is actually in the equation. Ka, water is not in the equation. It's included in this term Ka. So we basically have the conjugate acid and the conjugate base in the numerator, and then we have the original acid in the denominator. So I'm not sure if you remember, but when we had a very strong acid, then our products were favored. If we had a very strong acid, then that meant our numerator was big. And if we had a very strong acid, that meant our Ka value was larger than 1. If our acid is strong, it is going to be very likely to donate that proton. Therefore, is going to create a lot of product. And that is because our conjugate base is very stable. And that means that the concentration of our conjugate base and our conjugate acid are large. And so then that means that we have a numerator that is large in our Ka value, which means that we have a Ka value which is bigger than 1. If, however, our acid is weak and it's not likely to give up a proton, then it's going to stay here, and therefore our reactants are going to be favored, which means that the denominator is going to be larger, which means that our Ka value is going to be smaller than 1. So if we have Ka that is much greater than 1, we have a strong acid and products are favored. Whereas if we have a Ka that is much less than 1, then we have a weak acid and reactants are favored. So Ka values range from 1.0 times 10 to the negative 50th to 1.0 times 10 to the 10th. And so these values are sometimes a little bit confusing to work with. So what we do is we convert this Ka value to the pKa. That term P here means negative log. And so if we take the Ka and take the negative log of that, our values now are going to range from negative 10 to 50. And that's an easier number for me to grasp. I hope it's the same for you. So if Ka is the concentration of the products over the concentration of the reactants, then pKa is the negative log of that value. And so we're going to have values from negative 10 to 50. Now remember, a Ka that is very large means that you have a strong acid. So if we take the negative log of that value, it turns out that the lower the number, the stronger the acid, and that's because of the negative sign. So a low pKa value is a stronger acid. So like I said said, pKa values range from -10 to 50, and the lower the pKa, the stronger the acid. Just a little bit more information. Every pKa unit represents an order of magnitude or a power of 10. For example, H2SO4 has a pKa of -9, and that is 100 times stronger than HCl, which is a pKa of -7. You can also use the pKa to talk about the strengths of bases, because if we're looking at the conjugate base, it's an inverse. So if we have something that is a very strong acid and it donates its proton, we create a very weak conjugate base. Whereas if we have a compound that is a very weak acid with a pKa of 50, once we give up that proton, we're creating a very, very strong base. So it's the opposite. When you have a strong acid, it's going to make a weak conjugate base. When you have a weak acid, it's going to make a strong conjugate base. Basically, the stronger the acid, the weaker its conjugate base. And here's the table that I provided on the back of your periodic table the first day of class. And on this table, we have the acid, we have the pKa value, and we have its conjugate base down here. So this video is focusing on the pKa values, the numerical values that have been calculated for each of these acids, and it puts it in this table in order of increasing acidity. We walk all the way through from HCl, which is one of the strongest acids with a pKa of -7, all the way to ethane, shown down here, where the pKa is 50. Alkanes are incredibly weak acids. And I want to let you know that we can use the pKa values to predict which direction the equilibrium is going to be favored. If we have an acid that's on the left-hand side of the reaction with a pKa of 15.7 and an acid on the right-hand side of the reaction with a pK of 18, this is the stronger acid. And so this is the direction that's going to be favored. So we're going to have a Ka value that is a little bit higher than 1, and therefore we're going to have a little bit lower of a pKa. And so the direction of this reaction is going to be in the favor of the products, because this is a stronger acid. Equilibrium always favors the formation of the weaker acid and the weaker base. In a different video, we will discuss why the conjugate base is so stable using the ARIO method. Even though this is a beautiful table and it summarizes everything, I'm hoping that once we start talking about the structure of the conjugate base, that some of this will just become second nature. There you have it, looking quantitatively at acid strength using pKa.